joint work with Ritter and Bernhard Nebel, and it is about a token protocol for epistemic implicit coordination planning. So I want to start with an example that some of you might already know from the epistemic planning tutorial. Here, Bob wants to borrow Anne's apartment while she's away, and Anne can leave the key behind for Bob to pick up. And there are actually two possibilities. So she could leave it under the doormat, or she could leave it in the flower pot. Now, one plan for Anne, for Bob to get the key, is that she leaves the key under the doormat, and then Bob just takes the key from under the doormat. While this works from an omniscient observer's perspective, it does not work from Bob's perspective. Why is this the case? Because at execution time, Bob would not know where the key is. A better plan would be that after Anne leaves the key under the doormat, she tells Bob that it is there. Because she could, for example, call him. And then if he arrives, he can take the key from under the doormat. So when it's Bob's turn, Bob knows that his action is applicable and makes progress towards the goal. And this is actually the basic idea that our plans always have to satisfy. At plan time, it must be clear that at execution time, when following the plan, everybody knows that their actions are applicable and that they would make progress towards the goal. So how do we usually implement that? So we use dynamic epistemic logic, meaning epistemic states and action models. I don't think it's very important that, so probably a lot of you have seen this stuff already. I don't think it's important that you all understand it in detail. Basically, our states are Kripke states. So this could be here an initial state where it's common knowledge that N has the key. There is only one world. This would be an action where Anne actually puts the key under the mat, but Bob considers it also possible that she has instead put the key in the pot. And if we apply this action to this state, we get a new state where the key is actually under the mat, but Bob considers it possible that it's in the flower pot. Then our plans are strong uniform policies. And this strength is based on subjective reachability. I'll now show you what I mean by this using our example. So this was the unsuccessful plan. So Anne puts the key under the mat and Bob in the resulting state takes it from the mat. Now you could think, okay, that works. But actually our notion works from the subjective perspective of each agent, and we have to, it has to satisfy uniformity. So actually Bob in the second state, he considers it possible that the actual state is a state where the key is in the flower pot. And by uniformity, he would have to assign the same action to this state. And now depending on how we have modeled this action, it might be either not applicable or it might not yield the correct result. So this is not a plan that works. If we add the communication action where Anne announces the key is under the mat, then Bob performs this action take from mat in a state where he completely knows it works, so everything is fine. What could be done as well is we could give Bob a sensing action that he can apply after Anne's action. And then depending on the actual state, Bob would either sense that the key is in the mat or the key is in the pot, and he could react accordingly with an appropriate action, taking it from there. Okay, to recap, after implicit coordination means that after I've done my action, the next agent I expect to act knows that they can do what I expect them to do, and that this will make progress towards the goal. What it does not mean is that they actually intend to do what I expect them to do, because still every agent searches for its own plans. And now the big question is, can we guarantee that agents acting with respect to such plans always achieve the goal? Before I will bring an example, I want to make our assumption even more clear. So the assumption is each agent finds a policy by itself that could possibly include other agents' actions. And then at execution time, this policy profile, meaning one such policy for each of the agents, is executed in an interleaved manner. So if two agents have different policies and they both want to perform an action in a given state, then we just have to look at both interleavings, the one where the one agent starts with his action and the one where the other agent starts with its action. And then we consider an execution to be successful if it is finite and if it ends in a goal state. And for simplicity, for now, we assume that agents acts on maximal policies, and these are just policies that are defined on all states more or less in the state space from advanced. So we don't have to consider the possibility if some agent does something unexpected. We will do this later when considering replanning, because these maximal policies, computing them can clearly be very expensive. Okay, now the example. So we've actually already identified this problem and this example in an earlier paper. And here we have two agents and a lever, and the lever can be in 5 distinct configurations. And there are 2 potential goal configurations. One is fully to the left and one is fully to the right. The left agent can also only pull to the left, and the right agent can only pull to the right. To make this epistemically interesting, the left agent only knows for sure that the left configuration is actually a goal configuration. The right configuration might be a goal configuration, but it might also be not. And symmetrically, the right agent, he only knows about the right configuration being a correct goal, and the left one might be one, it might be not one. And now, because the agent always have to have uniform policies, and they always have to consider the worst case, the left agent has no other possibility than trying to pull the lever all the way to his side, because everything else could be a non-goal state. And for the right agent, it is the other way around. So he always wants to pull it to his side. And now it's very easy to see that if both agents always want to pull the lever to their sides, there are infinitely many executions, and all of them are infinite with the agents pulling the lever forth and back. So even if they manage in an execution to reach a goal state, the other agent, he will still want to pull the lever back from this state. So the problem that we had here is that agents can get in the way of each other, even if they act with respect to policies that they consider to be optimal from their subjective, imperfect perspective. The idea, what we had to solve this issue is to introduce a token protocol, and it's kind of motivated by something that is sometimes done in kindergarten or in elementary school, when the teacher wants to make sure that only one pupil speaks at a time. And then there might be a token, for example, a ball that the teacher gives one of the students, and only the student who has the ball is allowed to talk. And once the student is finished, he can pass it on to the next student. And in our case, the idea is identical. So only the agent that has the token is now not the agent that is allowed to talk, but the agent that is allowed to perform an action. And it's very easy to implement this for a given planning task, because we can just add a token possession fluent, which we make a precondition of each action. And then we add an action for initially taking the token and for an agent passing it along to the next agent. So if we look at the lever example, we can see that this simply solves the problem. So in the beginning, of course, both agents still think they are the only ones who can solve the problem, and they want to pull, or they want to get the token. So one agent, he just gets the token. And then afterwards, this agent will pull the lever to his goal configuration, and he will just keep the token because he has no reason to give it away anymore. So either the problem will end with the lever being on the left side, or it will end with the lever being on the right side. And there is no potential for infinite executions. So in our paper, we have proven theoretical results that hold in general. The first one is about a finite of executions. Can we guarantee using tokenized planning tasks that executions are always finite? And as it turns out, we can make this guarantee, assuming that all agents act indeed on maximal strong policies, and that they at least choose plans that are optimal from their subjective perspective. So what this definition of subjective optimality means is kind of a little complicated, because it's a perspective sensitive definition and it's kind of recursive. So I'll just give you the reference to the paper where we defined it. Now that we know that we can actually prevent executions to be infinite, we of course also want to know whether all of the policies of the original task are still preserved under tokenization, meaning that there is a corresponding strong policy in the tokenized task. And as it turns out, this is not always the case, but we can define a property which we call the knows the next agent property. If this property holds, then it's guaranteed that the policy will also have a corresponding strong policy in the tokenized task. And what this policy actually says, it's quite simple, that after each action that is applied by an agent, this agent will have to know to whom he can safely pass the token, no matter what outcome the action had. So for each outcome, it has to be clear for the agent who to pass the token. Of course, if none of the policies of the original task satisfy this property, then policy existence may be lost. An example where policy might be lost would be if I don't know which of my two friends wants a beer, and I just put it on the table for the correct friend to pick it up. Without tokens, this works perfectly well. The correct friend can pick it up, but with tokens, I would not know to whom to pass the token. Of course, it depends then on the exact modeling and on what the knowledge of my friends is. Maybe the friend could then pass on the token to the other friend, but this would then be a completely different policy. It's also not clear whether the friend has the necessary knowledge. It depends on how we exactly model this problem. So our positive result about preventing infinite executions was based on the assumption that all agents act with respect to maximal strong policies. But I've already told you that maximal strong policies, it's kind of a very optimistic assumption. You have to plan for the whole state space in advance. Sometimes, or often, you just cannot do that. So the question is, what about re-planning agents? As it turns out, it's a little more complicated with re-planning agents. And I have the following example here. So here we have two agents, and there is a building in between the agents. And the building is just high enough that each agent cannot see what happens on the other side of the building. So there is a ball, and the goal is that the ball ends up on the roof. And only the right agent can aim well. So if the left agent kicks, then the ball might end up on the roof, or it might end up on the side of the right agent. But if the right agent then kicks, then the ball will certainly land on the roof and the agents are finished. So if we look at this in terms of agent indistinguishability, so these are the two states that the right agent cannot distinguish between, because the ball is still on the side of the left agent or already on the top of the building without flying over. And these are the states that the left agent cannot distinguish between, because he has shot the ball and now it might already have landed on the roof, or it might be with the right agent, or the right agent might have already kicked it and now it's on the roof. And interestingly, this is a depiction both of the state space and of a strong policy for both of the agents. Since both agents will find exactly these policies, it is also clear that the execution will be successful. If we add tokens, not much will change, because then in the beginning, just the first agent, the left one, grabs the token, and then after shooting, he will pass the token to the right agent, and everything will work out because the right agent, he won't search for a new plan, even in the case here where the ball ended up on the roof. But the question is, what if we had replanning agent? And if we had reagent planning agents, then one could argue, okay, now the right agent has a problem. He has a token and he does not know that the ball is on the roof and that it is not with the left agent. And this holds for both agents. So both agents do not know that the goal has already been reached, and they consider possible that the other agent still has something to do. So because this is the case, they think that the other agent still might have some work to do. They will just pass the token back and forth infinitely. So we have actually a goal state, but we have infinite executions with passing the tokens. So the way we could prevent such situations is by requiring the last agent who acts to actually know that the goal has been reached. If we have already a tokenized task, it's quite easy. Then we can just modify the goal formula from, say, gamma to the agent who has the token knows that gamma. And in this particular example here, this would actually mean that there is no more solution for this problem. But you could very well imagine a slightly extended version of this problem where the left agent has another action in which he can throw the ball instead of kicking it. And this throwing action, it would be an action where he can safely, it is clearly that he will reach the other agent with his throw, and then he would have two plans. One plan would be first insecure kick, and then the other agent might have to kick again. And the second plan would be first he throws, and then certainly the other agent would throw. And with our modified goal formula, actually the insecure plan that can lead to infinite executions would not be a valid plan anymore, and the safe plan, it would still remain a valid plan. So one thing I should notice here is that if our agents would be really intelligent, then the right agent might actually infer when he gets the token from the left agent that this must have been because the left agent has already performed his kick action. But currently we are making assumption that the knowledge state of the agents is exactly described by the actions from our planning tasks. So the right agent cannot make this inference. And this forward induction is actually kind of quite difficult. We already tried something out and it's still future work. So to sum everything up, we defined tokenization in our framework. We saw that if agents use maximal policies, then tokenization prevents infinite executions. However, the existence of policy in the original task is only preserved for the tokenized task if this knows the next agent property holds. Also, we can apply tokenization to replanning agents, but we then have to make a modification such that we don't get infinite token passings. Thank you.